Hello and welcome, everyone. My name is Dane Menke. I am the Digital Marketing Manager here at Regenesis and Land Science. Before we get started, I have just a few administrative items to cover. Since we're trying to keep this under an hour, today's presentation will be conducted with the audience audio settings on mute. This will minimize unwanted background noise from the large number of participants joining us today. If the webinar or audio quality degrades, please try refreshing your browser. If that does not fix the issue, please disconnect and repeat the original login steps to rejoin the webcast. If you have a question, we encourage you to ask it using the question feature located on the webinar panel. We'll collect your questions and do our best to answer them at the end of the presentation. If we do not address your question, we'll make an effort to follow up with you after the webinar. We are recording this webinar, and a link to the recording will be emailed to you once it is available. In order to continue to sponsor events that are of value and worthy of your time, we will be sending out a brief survey following the webinar to get your feedback. Today's webinar will discuss prioritizing actions to address exposure to PFAS. With that, I'd like to introduce our presenters for today. We are pleased to have with us Dr. Ali Ling, Assistant Professor of Civil Engineering at the University of St. Thomas. Ali Ling's career includes 9 years of consulting experience and has focused on using basic science concepts to solve complex engineering problems. Her current research interests include engineered circularity, PFAS treatment and source reduction, and microbial ecology of engineered systems. We're also pleased to have with us today Dr. Paul Erickson, Vice President of Research and Development at Regenesis. Paul Erickson oversees the commercialization of new environmental solutions to address complex remediation challenges. In his time with Regenesis, he has led the development of a number of remediation products and technologies, including Petrofix, Aquafix, SourceStop, and Flux Tracer. All right, that concludes our introduction. So now I will hand things over to Dr. Ali Ling to get us started.
Thanks for the intro, Dane. I'm going to start by just giving a brief rundown of where we're going today. First, I want to talk about what makes PFAS unique as an environmental hazard. And then I'll talk about a global mass balance concept and some steady state treatment costs. I want to talk a little bit about PFAS use restrictions because that's kind of the direction where I think the cost data is driving us, and some big picture cost considerations. And then towards the end, I'll talk about PFAS exposures and prioritizing actions as a society to try to manage those and which sorts of things should be falling out on top. So I know many of you know a lot about PFAS. I do want to kind of highlight some of the key things that I think make PFAS unique as an environmental hazard and how that influences what we're going to do about them. So the first thing is that they're persistent and mobile. I think most people know this, but I just wanted to include this graph from a recent paper. This compares PFOA and PFOS to a whole bunch of other recent environmental contaminants that we've dealt with as society. So the x-axis shows global cumulative production, which I'm less concerned about, but the y-axis shows overall persistence in terms of years that it lasts in the environment. I'm assuming that the authors just kind of threw up their hands and put PFOA and PFOS up there as high as the units go. But what I'm trying to highlight here is there's other things that are somewhat persistent and mobile, but PFAS are really off the chart in terms of how persistent they are and how difficult they are to remove from the environment. There is no known mechanism to remove them from the environment using natural processes. So of course that affects the environmental fate in transport, in that the fate is that it doesn't ever go away, but also the mobility affects where it moves. It moves a lot in the air phase and it stays in the water phase. The other thing about persistence is that it really affects future generations, so that any actions we take now to manage or not manage PFAS is going to have an outsized effect on future generations just because it is so persistent. PFAS are also very ubiquitous. So this picture was taken in my home. I just spent like 30 minutes walking around and coming up with the types of things that typically have PFAS in them. So clothes, we've got paper, electronics, cookware, Band-Aids. There's a lot of things. And when we're thinking about all of the things that PFAS are used in, it's difficult to think about trying to phase them out from products because they're just so ubiquitous. It's not going to be like phasing out chlorofluorocarbons from refrigerants because PFAS are just everywhere. It's going to be much bigger lift to do that. I just want to mention that this is stuff that was in my house. This doesn't include things like building materials and outdoor equipment, and it doesn't include things like food or food packaging, which it turns out are a really big source of exposure to humans. The third thing I want to highlight about PFAS is that they're really numerous. There are so many of them. There's a couple of different ways that people define them, but somewhere between tens of thousands to millions of PFAS are in use. And we in the remediation world often talk about perfluoroalkyl acids, or PFAS. That's this category of them. Things like PFOA, PFOS, PFBA. Those PFAS account for less than 1% of global use. So even though that's the types of things we're used to measuring in remediation settings, they're not very important in terms of how much we're using and emitting right now. Most of the current uses and emissions are in fluorinated gases, many of which degrade to trifluoroacetate, or TFA, and often those have largely unknown health effects and long-term implications. So other things that are complicated about having lots of compounds, they're relatively hard to measure just because there's so many of them. So as a result, there's a lot of uncertainty. So most toxicity treatment and fate data is for PFAS like PFOS and PFOA, but we don't necessarily know how toxic are all the other PFAS because there's so many of them. There is a moderate amount of work going in a field called cheminformatics to help try to predict toxicity and fate of other compounds that we might not actually have experimental data for, but there's more uncertainty there. The other complication here is that it's really difficult to close the fluorine mass balance due to analytical limitations in some different phases. So because there's so many PFAS, it's really difficult to say whether all of the PFAS are removed. We can measure the certain targeted PFAS from certain analyses, but PFAS, not only are they mobile, they also are able to switch into other types of PFAS through different degradation processes. So we might be making different types of PFAS, but not measuring them with different analytical processes. So it makes things complicated. The reason, I know many of you are remediation professionals who know a lot about PFAS, but I just wanted to highlight that persistence and mobility, ubiquity, and how numerous they are really make them very challenging as an environmental contaminant. I'm going to talk a little bit about a global mass balance on PFAS in the environment, and some costs that I recently estimated at how much it would cost to keep that massive PFAS in the environment steady. So I talked a little bit about persistence and how persistent they are. I'm going to make the argument here that persistence is as important, or even potentially more important, than toxicity when we think about how problematic an environmental pollutant is. So if we think about a global PFAS stocks in the environment as kind of this greenness of this world here, we have ongoing emissions of PFAS, and if they're persistent and there's nowhere for them to go once they're into the environment, we're going to keep seeing increasing mass stocks and concentrations in environmental media, and an increased potential to exceed both known and unknown thresholds to impact human health and environmental health. So if they're so persistent, they don't degrade in the environment, it almost doesn't matter how toxic they are, because if we keep making them and making them and making them, and we want people to live on the earth, hopefully indefinitely, at some point, the concentration is going to exceed whatever the toxic threshold is. So persistence is really a problem, and it's fairly unique for PFAS and some other very persistent substances about what we can do about it. I'm going to talk a little bit more about this mass balance, and I'm going to transition into talking about it like a bathtub. So if the amount of water in the bath is reflecting how much PFAS is present in the global environment, and then the tap reflects the emissions. By contrast, if we talk about active treatment and destruction of PFAS from environmental media, that's a very small amount right now. Right now, that's media that's being sent to high temperature thermal processes, a very small amount that's being sent to other processes being developed. But by and large, active treatment and destruction is basically negligible when compared to how much PFAS we are putting into the environment. So if we think about PFAS as the amount of water in the tub, if we want that amount to stay constant and not overflow, there are a couple different options that you could do. The first thing you could do is you could increase treatment to match emissions, so that the amount coming in is the same as the amount going out. You're just putting in a lot of effort to do more active treatment and destruction, and thus the water level in the tub stays low. And then once you get to this point, theoretically, you could start drawing down the massive PFAS in the environment. The other thing you can do is to significantly reduce PFAS made, used, and emitted. This would be reducing the emissions rate to near zero, or some small amount, ideally to match active treatment and destruction. I'm going to argue that this is the route we should go, but unfortunately, there's not a lot of data to support how much this would actually cost. So instead, I wanted to ask the question of how much would it cost to increase treatment to match emissions, and kind of use that as a bookend of, is this a reasonable amount that we could even do this for, or should we be focusing more on reducing emissions? So how much would it cost to increase treatment to match current emission rates? The process I went through for this is to estimate how much PFAS are currently emitted from all sources globally. I looked at the different technologies that are currently demonstrated at available and relevant scale. And then for those technologies, I asked how much does it cost to destroy a kilogram of PFAS, starting from environmental media for each technology. So the math that went into this would be global costs for steady state PFAS would be the emissions in mass per year times the technology application costs in costs per mass of PFAS, and then you would get steady state in terms of how much it would cost per year to maintain that steady state conditions. And I'm going to put a spoiler here, it does exceed the global GDP. So let's talk through the details here. So first, I wanted to ask the cost for what type of PFAS. Ideally, I would like to ask the question about in all PFAS because all PFAS are persistent, thus all PFAS are a problem. However, I start by targeting PFAS because there are established technologies to treat them, including studies that are measuring their removal from one side to the other, and they're more widely reported and measured in treatment applications. So I would like to be able to estimate costs for all PFAS, but it's really difficult, if not impossible, to do it for all PFAS. So I'm just starting with PFAS. So I looked at different studies, both on the emissions and the destruction side. On the emission side, the amount of PFAS production in emission per year is probably between 1,000 to 10,000 tons per year globally. And then on the active treatment and destruction cost side, I looked across a range of media. So starting with landfill leachate, which is a concentrated thing and kind of on the lower side of costs per mass to treat, all the way up to drinking water treatment, which is a very dilute stream of PFAS and thus costs a lot because we have to treat a lot of volume to remove a kilogram of PFAS. So the active treatment and destruction costs are on the order of around 1 to 100 million USD per kilogram. The numbers that I actually used in the study were 0.9 to 65 based on the specific 5 or 10 different case studies of costs that I looked at. So multiply these two numbers together, you get a cost of about $1 trillion to $600 trillion per year for PFAS alone to remove them from the environment as fast as we're currently emitting them. And for context, the global GDP is about 106 trillion. Okay, so that's for PFAS alone. What about if we think about all PFAS? This isn't super easy to do because, again, there's a lot of complications, but I just wanted to get a very rough number here. So if we're talking about PFAS rates, that number of 1 to 600 trillion per year. If we're talking about total PFAS, remember PFAS are only about 1% of total production in the world. So if we multiply that number by 100, that's about total PFAS emissions versus PFAS emissions. And then other PFAS that are not PFAS are often more costly to separate from the environment. They might be, shorter chains or more mobile such that they stick to GAC less or other things. So again, this is very rough, but if we multiply that number by these numbers, we get a number of 200 trillion to 100,000 trillion. That's 100 quadrillion US dollars per year for all PFAS. I know that's a really big range and there's a lot of assumptions there, but I think we can all agree that this is too expensive. This is too much. There's not enough money in the world to remove PFAS from the environment as fast as we are adding it right now. And it's not even close. So we can throw up our hands and just say this is hopeless, or we can pivot and think about the other option to get to steady state, which is PFAS use restrictions and reducing how much we're actually using and emitting to the environment. So I'm going to talk a little bit about the regulatory status of current PFAS use restrictions, which I think is the response to this study. If we can't afford to remove them from the environment once we're there, we need to not put them into the environment in the first place if we ever want to have a world where environmental PFAS contamination is not a huge problem. Okay, so options for reducing emissions. To reduce current and future exposures, we need to significantly reduce PFAS made, used, and emitted. Turn the tap down instead of trying to open the drain more. So some key ways to do this. The first is to reduce PFAS use in products, which is PFAS use restrictions. That's what I'm going to be focusing on here. Another approach here is to reduce PFAS emissions from point sources. So that is, there's places where we might still need to be using PFAS in the future, but if we can reduce the emissions from those uses as much as possible, that's going to have a big impact on environmental PFAS as well. Some places where this can happen is NPDES pretreatment or water resource recovery facilities. If you're treating the wastewater before it gets to those facilities, if it's at a concentrated form, you can reduce the PFAS emissions there, potentially like at the source. Also air emission control, if you have a facility that's managing a lot of PFAS or using a lot of PFAS, controlling the air emissions of them. And then the wastewater part also includes landfill leachate as a potential concentrated source that would be less expensive to treat per volume. So now I'm going to focus on number one for the rest here, thinking about PFAS use restrictions. This is a figure from Safer States, which is an organization that is tracking these online, but there's about 34 states with a bunch of policies to protect and limit PFAS, and these are growing a little bit. I'm going to talk a little bit more about Minnesota in a couple slides, but when we think about PFAS use restrictions, it's important to think about what are people going to use instead of PFAS. So I made this little sketch here that highlights some of the key product areas where there are readily available alternatives to PFAS that don't have necessarily a significant change in performance here. So things like food packaging, firefighting foams, textiles and apparels, carpets, furniture, children's products, cookware, ski wax, cosmetics, and menstrual products. These are all areas where we have other options. So in these types of areas where we don't need to be using PFAS, I would argue that we really should not be using PFAS there, and we should try to phase them out as fast as possible if we have alternatives available. Now, thinking high level about PFAS use restrictions, there's two main things that I think are very important. The first is to regulate PFAS as a class. If you buy nonstick frying pans, you might go out and see some nonstick frying pans that say PFOA free. Well, great, PFOA hasn't been made in the United States for a decade, so it's not surprising that it's PFOA free, but what does it use instead? Does it use PFHXA? Does it use some other type of PFAS? If you regulate just one PFAS at a time, you get this whack-a-mole situation where companies move from one PFAS to the other, and you're not actually addressing the problem of PFAS persistent. So if we regulate them as a class, because all of them are persistent, that helps manage the problem of just switching to other types of chemicals. And then thinking about what the alternatives are and whether they're regrettable too. The second thing here is considering currently unavoidable uses. So there might be some places where using PFAS actually provides more benefit to society right now than not using it. So including derogations or exemptions for essential uses to limit the immediate impact on economic engines and society. So there are some places where this, I think, will be useful, and there should be ongoing reevaluation of those uses and investment in development in chemical engineering to develop those non-PFAS alternatives in places where they are currently unavoidable. I like the use of the word currently unavoidable instead of essential because it implies that that could change over time. If, as we develop new alternatives, they might not be unavoidable anymore. I want to talk a little bit about Minnesota's PFAS use restrictions, partly because Minnesota is a leader in the world here, and also because I'm from Minnesota, and so I'm very excited about it. But Minnesota has a ban in place on intentionally added PFAS in food packaging, and then by 2025, we'll be banning intentionally added PFAS in 11 product categories, including the ones that I showed on a previous slide. Starting in 2026, there will be additional reporting requirements for PFAS in products. And then starting in 2032, Minnesota will ban the use of PFAS in all products where the use is not currently unavoidable. So I want to talk a little bit about two nuances here. The first is this intentionally added. So again, here's my picture of PFAS uses in my house. And the tricky thing here is most PFAS are probably not intentionally added. They're so pervasive in our supply chain. Companies that are making products, sometimes they have visibility into like the first tier of their suppliers, like the people who are giving them components to put into their products, but they usually don't have any variability into tier 2, tier 3, into the suppliers for the suppliers, or the suppliers to the suppliers to the suppliers. So there are potentially a lot of places where people do not know that they have PFAS in their products, but they actually do. So one example from Keen Footwear, which is a US-based company that phased PFAS out of their products about 5 years ago, they had a case study where they said they were going through this process and they found 100 different components of their footwear that had PFAS in it before they phased them out. And that is astounding to me that you can try to phase them out of this one type of product, and there's so many different things that have PFAS in them once you go backwards and dig into them. So part of the issues with intentionally added is that removing PFAS from supply chain actually requires companies to first identify PFAS in their supply chain, because you can't remove it if you don't know it's there. Some regulatory ways to get here are to provide reporting requirements. So for the Minnesota PFAS ban, there's additional reporting of PFAS in supply chain that will be starting in 2026, where companies selling products in Minnesota will need to be reporting how much PFAS are in their products, what PFAS, and what they know about it. And then there's federal requirements under the Toxic Substances Control Act, which is more waste focused, but I think will also help incentivize suppliers to help understand their supply chains a little bit better. So this data will be collected, including PFAS types, amount used, products, worker exposure, and fate disposal. I think there was recently an update here that people don't have to go back to 2011. I don't remember what the update was, but there is an update to this. But overall, I think different reporting requirements by both state and federal agencies are a driver to help companies try to understand the PFAS in their supply chains as a first step to phasing them out. The next complication of PFAS use restrictions I want to talk about is this currently unavoidable use. So the Minnesota Pollution Control Agency is working on determining what is currently unavoidable before that 2032 deadline, and they will be accepting applications to be listed as currently unavoidable from different companies that are making products. So some of the background for this is it's kind of related to the essential use from the Montreal Protocol, which is an international agreement that's been used to phase out other chemicals in the past. And that essential use means that it's necessary for health and safety or functioning of society, and also that there are no technically and economically feasible alternatives. So it's kind of those two things. It's like, how important is it? And then is there something else to do for it? And if there's not, that's kind of where chemical engineering development comes in. And there is a moderate amount of literature out there about applying the essential use concept to PFAS. So if you're interested in this concept, I encourage you to check out some of that. If you are interested in use restrictions, I find this area fascinating, but I just wanted to include some sources here. The OECD international group has a portal on PFAS alternatives that are currently available. ChemSec, which is a European organization, has some tools to help identify products that might have PFAS in them, as well as a marketplace to identify vendors for parts and components that don't have PFAS. And then the European Union's REACH documents. This is the most comprehensive PFAS use restriction that has been proposed. And this document is a detailed proposal for those restrictions, including appendices on PFAS uses and economic impacts of those proposed restrictions. I'm following this one really closely because the European Chemical Agency, or ECHA, is currently working on developing cost estimates for what sorts of societal impacts these use restrictions would have. And I think those costs will be very important to compare to the remedial costs to try to understand and prioritize and justify some of these PFAS use restrictions. All right, so that's kind of the global picture in terms of PFAS, mass balances, remediation costs, and then the status of use restrictions. I want to talk a little bit about prioritization. I think in the professional realm, especially in academia, sometimes people have the thing that they do or the thing that they're interested in, and it's very easy to fall into the trap of feeling like this is the most important thing in the world. And of course, I think my thing is the most important thing in the world too, so I'm of course biased, but I want to talk a little bit about how we can better understand and prioritize actions to address exposure to PFAS. And the high level message here is if we're prioritizing actions for human health and well-being, it's like PFAS are a problem, but they're not actually like the biggest problem in the world. Like climate is the biggest problem in the world. So I think if we're talking about PFAS in the context of environmental pollution, thinking about where PFAS fits in the context of problems and also where specific actions to PFAS fit within the context of those problems. So one of the things we ask when we're trying to prioritize things is we ask, how much does it cost? But I think it's important to ask, how much does what cost? What is it that we're trying to buy with our investments, especially in treatment options? So typically, if we are undergoing environmental remediation or treatment, we are targeting improvements to current human health risks, as well as future human health risks. So I'll talk about current human health risks in a minute, but future human health risks are more related to the buildup of PFAS in the environment and potential for future exposures. So let's look at current human health risk. This data is from a review by De Silva from 2021, and this looks at a bunch of different studies that estimated the contributions to human exposure in certain communities for PFOA by different sources and medium. You can see the green part here shows how much PFAS is coming from drinking water, and the orange one shows how much of it is coming from your diet. So generally, about less than 20% of PFAS exposures to most humans is coming from drinking water. Now, there are definitely communities, including ones in the United States, that have specifically contaminated drinking water sources where this number is going to be higher. But as a whole, for humanity, for Americans as well as other places in the world, generally the amount of PFAS you're getting from drinking water is relatively small. Most of the PFAS that you're getting is through food ingestion and also through dust inhalation. And these things are more related to PFAS in products that we buy and bring into our homes than they are to environmental contamination. Now, I know I'm probably talking to a virtual room full of remediation professionals, What I'm getting at here is that the remediation work we do about environmental contamination out there is not the most important thing to managing human health risk from PFAS. The most important thing to managing human health risk from PFAS is trying to reduce how much of it is in the products we use, how much of it gets into the food that we eat. There is a place for environmental remediation. We'll talk about that. But if we're thinking about current human health risks, environmental remediation is not that important. Now, I want to talk a little bit about phase out and potential impacts on human health risks. So this graph shows concentrations of some measured PFAS in blood serum in the United States. This is from the CDC studies that have been ongoing on human exposure to environmental chemicals. So on the x-axis, you can see different years where the study was conducted, and then the y-axis shows average serum concentrations in the US from those studied. And you can see the PFOS concentration especially drops quite a bit from about 2000 to about 2018. And this is coincident with the phase out of PFOA and PFOS in the United States, which happened between about 2000 and 2015. So those concentrations have decreased over time. Concentrations of TFA and some short chains are largely unmonitored, so I would be very interested to see what those are, but I don't have the data on that. But my key takeaway from here is that if PFAS are phased out, the primary future exposure route may be from PFAS in the environment. If we phase them out, we're probably going to see less of it in our bloodstream because most of the exposures are from PFAS use. But for future human health risks, we should really be thinking about the environment. So talking about future human health risks as something that we could be buying with investments in PFAS remediation, we really are talking about environmental PFAS. And I established earlier that we cannot afford to increase remediation rates enough to match current emission rates. So what we need to do is prioritize what we do with the limited amount of funding that we have to address PFAS. This is the logo for 0PM, which is a Europe-based research and action organization that is focused on persistent and mobile substances, PM, and that includes PFAS as well as some others like 1,4-dioxane. But this organization is really focused on preventing as the first source here. And so when we think about, especially since they're so persistent, we need to prevent them from getting into the environment, otherwise they'll keep building up. So the high level argument here is that reducing PFAS use and emissions will have greater benefit per cost than remediation on reducing current and future human health risk. Now, I know this is a remediation presentation, so I want to acknowledge that what are we going to do about the PFAS already out there, especially in sites where there has been a specific contamination event and the concentrations might be significantly higher than environmental backgrounds. So I think there is a place for PFAS remediation in those types of sites, and I want to set a framework for thinking about them. So when we're thinking about environmental remediation of PFAS that is already out there in the environment, I like using this framework that thinks about different levels of PFAS removal. If we're comparing different types of technologies, we should be comparing apples to apples, or at least considering what is the final fate of the PFAS. So this is a scale that I'm proposing here from 0 to 3. Level 0 fate is that the PFAS is re-released to the environment. Level 1 would be the PFAS is sequestered for years or centuries to come. These two are kind of like moving PFAS from one place to the other, not necessarily destroying it. Once you get into level 2, that's kind of some PFAS destruction with an unknown amount of re-release, or level 3, full mineralization is likely or possible. Those are things where we're turning PFAS into something that is not a PFAS. So some of the technologies that map here, if we're thinking about level 0, that PFAS re-release, municipal waste incinerators are mostly doing this. They're not getting to a temperature high enough to actually destroy PFAS or make them not PFAS. And so in a lot of those systems, the PFAS are just going back into the atmosphere, into the stack. This also applies to if you have a drinking water treatment system that's using reverse osmosis to separate PFAS, and then you're sending that concentrate to a wastewater system, then that is going to pass through that system and just go back into the environment. Level 1 is the PFAS sequestration for years to centuries, and this includes things like landfills and also things like in situ sequestration, as well as deep well injection. Level 2 is kind of some PFAS destruction with unknown re-release. The technologies I put here are hazardous waste incinerators and thermal oxidizers. These thermal technologies that have primarily an air emission, one of the issues here is that we don't currently have analytical capabilities to close the fluorine mass balance on this type of process, especially with the air emissions, which means that we can measure for PFAS and they all go away, which is great, but it's hard to know exactly what they turn into. So that's why I'm listing those as level 2. And then level 3, where full mineralization is likely or possible. That includes a lot of developing PFAS destruction technologies. I know this is kind of an alphabet soup here, but things like hydrothermal alkaline treatment, or HALT, like supercritical water oxidation, or SQO, like UV advanced reduction processes, or UV ARPs, plasma. There's some other things that fall in here as well. So typically, depending on what we're trying to do, I often am advocating for level 2 or 3 management if it's affordable and if it makes sense for your site. But one of the complications here is, of course, you see increasing remediation costs as you get closer to that full mineralization. It costs a lot more to heat something to 1,000 degrees C for near full mineralization than it does to put it into a landfill or to put it back into your wastewater plant. So it is important when we're comparing costs to be considering what level we're at and making sure that we understand that and how that affects potential future risk. So again, a complication with level 3 is that full destruction from environmental and media can be very expensive and doesn't necessarily make sense for all sites. So are there applications where level 1 sequestration makes sense from a cost benefit perspective? Could you see more benefit in terms of reductions in current and future human health risk by sequestering PFAS in a way that's reducing exposures than you might see from some sort of a more intense treatment that would be more expensive? So talking about some of these level 1 options that are in situ, the first one is in situ sorption using colloidal activated carbon. Things that you would need to better understand to understand long-term risks would be the understanding the duration of sorption and capacity. And then the other option here would be kind of partial biodegradation in situ, in which case you would need to understand the toxicity of end products. I say partial biodegradation because I have not seen any convincing evidence that it is possible to turn PFAS into something that is not PFAS using biological means. And that's partly a thermodynamic limitation. If somebody has evidence to the contrary and thinks that you can degrade PFAS fully in the environment to non-PFAS endpoints, I would be very happy to see that because I love microbes and would love to see news of that. But as of what I know right now, I do not think that is possible. So if we're talking about in situ biodegradation, we're talking about hopefully turning more toxic PFAS into less toxic PFAS. There's a moderate amount of work being done here right now, but the need there is really to understand what are the PFAS you're starting with, what are the end products coming out, and what are the potential toxicities of those. Are you really seeing a benefit in terms of potential exposure and toxicity there? So focusing on the colloidal activated carbon, which is Regenesis plume stop technology. Again, the question here for level 1 technologies is, are there places where the difference in cost is enough to make it worthwhile to just sequester it instead of taking everything out and destroying it? So this study was done by Ramboll in collaboration with Regenesis, and they looked at a contaminated groundwater site, and they looked at preliminary design of a pump and treat system with granular activated carbon adsorption and a pump and treat system with foam fractionation versus immobilization with plume stop, which is that level 1 technology. I admit I don't actually remember what the final fate of the PFAS was in this technology, whether it was 1, 2, or 3, but it was ex situ treatment technology as opposed to an in situ technology for the pump and treat options. So the study compared costs in greenhouse gas productions for these 3 different options, and the plume stop had about 40% of the cost of pump and treat and only about 3% of the carbon footprint as a result of much lower energy use. So I think that makes the case where there might be some situations where the in situ sequestration might actually result in enough reduction in exposure and human health risk, given the lower costs, and you could potentially do that across a wider area and see more benefit per cost than with a pump and treat type of technology. So that's kind of the prioritization part. I want to just touch a little bit about, as a whole society all across the earth in terms of the massive PFAS out there, there's 3 main things we can do. The first is we could do nothing, which has costs in terms of health risks and environmental harm. Some recent studies estimated about $50 billion of costs annually for the US and the EU each for healthcare costs due to PFAS. And if we do nothing, those costs are going to increase because the amount of PFAS in the environment is also going to increase. Another thing we can do is to remediate it after release to the environment. So if we're looking at remediation and destruction, again, that's that $1 to $65 million per kilogram of PFAS. The costs for sequestration are somewhat less, but also, if we're looking at the global scale, we would need to prioritize these in places that have relatively high concentrations and relatively high risk for human exposures. And then the third option is to reduce PFAS use and emissions, which is, of course, the soapbox that I am standing on. The cost for this, again, the European Chemical Agency, ECHA, is evaluating these costs. as part of a economic and social analysis of the current proposed REACH restrictions for restricting PFAS across Europe. But I think we need to better understand those costs, and then we could compare those costs against the no action costs and the remediation costs. So what I'm looking at here is there's a framework here where we've got a triangle. And if we are thinking about PFAS on the global scale in terms of total mass of PFAS in the environment, any sort of action we take, any sort of project is going to fall somewhere within this triangle. So here's an example mapping of a specific project. I am starting from this PFAS use and emissions because this is kind of where I'm assuming the costs are going to be lowest. But anywhere you get away from emitting it to, if you get towards remediation or if you're not doing anything, you're going to be incurring societal costs of health and environmental impacts. You're going to be incurring societal costs, or potentially somebody else might pay for it for remediation. But I put together this triangle just as a framework for thinking of the different actions that we can take about PFAS and trying to think about specifically the costs and the balancing of the costs for specific actions and specific projects. So thanks for listening. My name is Ali Ling. I'm an assistant professor of civil engineering at the University of St. Thomas, and I am excited about trying to understand and prioritize different engineering technologies, including for PFAS. I'm going to hand things off to Dr. Paul Erickson with Regenesis, he's going to talk a little bit more about their technology.
Thanks, Ali, for the informative and important presentation. As Ali mentioned, I'll just quickly step through some of the work that we've been doing related to the treatment of PFAS that have been released to the environment. And here at Regenesis, we are a soil and groundwater remediation company. And the use case that I'll highlight here is, as you can see, an airport. And this was a place that a lot of AFFFs that contained PFAS were used and were land applied. And this is a situation that the contamination's already out there, so we're looking to have to deal with the mass weather in some way or another. And so, as Ali mentioned, there's sequestration technologies, which is what we have developed and we offer at Regenesis. And really, conceptually, it's keep the mass in place and not allow it to continue to disperse into the environment, go off-site and accumulate in other areas. When you've got an opportunity to contain the mass in the location that it exists, this is one viable remediation strategy that we've been working on for a number of years now and is at the commercial level and really gives one an opportunity to address these issues now versus waiting for some of these technologies to mature and the costs associated with them to come down. So we've been using PlumeStop now to treat PFAS for a number of years. We've done 55 applications across different places in the world thus far and have a number that are in the design phase right now. And what I'd like to do now is just take a moment and step through some of the, Ali's done a great job of kind of setting up what this type of approach, how it fits in with the remediation scheme, but I'll spend some time talking about that point a little bit more and then also highlight some of the research that's been done looking at colloidal carbon technologies for environmental remediation of PFAS. And so how does remediation with PlumeStop and these colloidal carbons fit into the scheme of PFAS? It's this idea of enhanced attenuation. So again, if you've got PFAS already located in soil and water, you can use what is already naturally occurring, which is adsorption onto soil organic matter and these other things. And you can enhance this process. And from a risk standpoint, this then takes the exposure pathway. If water is the matrix that then is carrying these contaminants away, and as Ali mentioned, for really highly contaminated sites, this is what then is driving the impacts to locations where you do have an actual source that is driving up water as one of the more important exposure pathways for folks living in an area. And anyways, Chuck Newell and GSI and his colleagues put together this publication a number of years ago that was looking at how this might look in terms of remediation. And they highlighted that of our options right now to treat PFAS, this, just given the costs associated with it, enhanced attenuation is an approach that makes sense. One of the ways that is commercially viable to do that right now is through this injection of particulate sorbents like PFAS. And they outline what that would look like and how that might fit into a remediation framework. So Specific to plume stop, there's been a number of publications that have demonstrated the technologies at work. And starting with this demonstration from 2018, the publication rather was from 2018. And Rick McGregor in Canada had one of the first sites where it was a former fire training area that the treatment was targeting petroleum hydrocarbons. There happened to also be PFAS present. They took samples and demonstrated that the PFAS was removed from the groundwater. And they reported on this in 2018. And really, this was one of the first publications demonstrating this approach in the field, and it's used to remove PFAS from groundwater. Building on that site, Grant Carey worked with Rick McGregor to demonstrate the longevity of treatments, specifically this particular Canadian example, and demonstrated that in certain situations, this sequestration using colloidal carbon, using plume stop, you're capable of getting treatment longevity on the order of decades. So this very much in Ali's scheme fits in that type 1 treatment, which can be a cost-effective means and cost-benefit analysis-wise, a strategy that makes a lot of sense to use. And moving on, as the number of sites that we've been working on have grown, we've worked with Grant and provided him with data to then go and look at some of these other situations. And they did a review a number of years ago in 2022, looking at 17 different sites, primarily on airports. Again, these are impacts from AFFFs primarily, and looking at some of the different aspects that will affect the longevity of these treatments, what will drive how long they last, the breakthrough times, et cetera, and some of the differences that come up between colloidal carbon and activated carbon, and how it looks different in an in situ process versus an above ground treatment. And that gets into which this publication walks through to some degree. It's about mass flux, and if you're not moving water quite as rapidly through in an in situ treatment versus a granular carbon above ground treatment, really what that means is that your mass flux looks very different, and so your treatment longevities look different as well. And last, I'll kind of finish on, particularly the DoD, but there's other entities out there that are funding research into remediation of PFAS. And this has been an ongoing effort now, according to this figure, since 2011, that the DoD, through CERTUP and ESTCP and other means, have been putting research efforts into understanding and developing technologies to remediate PFAS and destroy them, sequester them. And I highlighted here a few of the projects that are looking at specifically colloidal carbon, and we're involved in a number of these at the research level, where that's evaluating the factors that influence the longevity of these types of treatments. And then on the field demonstration side, what are the factors that influence bringing these technologies to the field, in addition to their scale up and factors that the Department of Defense is more interested in. And with that, I'll close and open things up for questions. Thank you for tuning in, and be happy to answer any questions.
All right, thank you, Paul. That does conclude the formal section of our presentation. So at this point, we'd like to shift into the question and answer portion of the webcast. Before we do this, just a couple quick reminders. First, we will be sending out a brief survey after the webinar. We really appreciate your feedback, so please take a minute to let us know how we did. Also, you will receive an email with the recording as soon as it is available. All right, so let's circle back to the questions here. Here's a question for Ali Ling. Ali, the question is, your cost estimate is based on current flows. What about existing stocks of PFAS? Does anyone know how much it would cost to remove all the PFAS that's currently in the environment now?
Yeah, that's a really good question. So part of the reason that I didn't answer that question is because I don't know if there's any way to answer that question right now. My paper looked at how much it would cost to remove PFAS from the environment at the same rate we're adding it right now. When we're talking about the stocks of PFAS that are already in the environment, we're talking about PFAS in groundwater, we're talking about PFAS in soils, we're talking about PFAS in the atmosphere. One of the reasons why that question is a challenge is that most of the PFAS out there in the world is kind of a background concentration at very low dilute concentrations. And removing those from the environment would be quite expensive, a lot more per mass of PFAS than the cost that I showed, just because it is so dilute in most environmental settings. And it's not only would it be so cost intensive, it doesn't make sense to remediate PFAS everywhere where it is. So I think, I don't think we have a good answer to that question, and I don't think that it's something we should try to do. I think what we should try to do is remediate the specific sites where there's a significant human health risk, but otherwise really focus on the PFAS use restrictions to limit human health risks.
All right, thank you. So here is another question. This one's for Paul. Paul, the question is, what has the regulatory acceptance been like for plume stop treatments for PFAS?
Generally positive. It depends on where the site comes up and where the question comes up, but overall, these aren't, once you kind of get into what the strategy is and how it looks compared to other contaminants. So for example, not quite the same, but similar as hexavalent chromium, there are other situations where the contaminants aren't degradable, they're left in place. Their state is perhaps changed, but radionuclide remediation is another example of where you're really counting on some type of sequestration. And with proper engineering controls and monitoring, it's typically, we don't have many issues in many situations that have come up.
All right, thank you, Paul. So here's another question here. This one's for Ali. Ali, the question is, how will emerging less expensive PFAS treatment technologies change the prioritization of PFAS management actions?
Yeah, I think there are emerging technologies coming out that are working better and being less expensive than the technologies that I evaluated in my cost estimate. But if you think about the staggering scale of costs, trillions to quadrillions of dollars for maintaining steady state, it really doesn't matter if you have technologies that are 100 times cheaper than the ones we have today. It's still unaffordable. It's still just a problem of we're making more than we're taking out. It's almost like the bathtub is overflowing and we're trying to invent all these fancy mops to try to mop up the bathtub instead of trying to just turn the tap off. And I acknowledge that turning the tap off is not as easy as just turning the tap off. But I think that emerging technologies, while they will be very helpful in specific applications where it makes sense to do treatment, I don't think that changes the picture on overall societal goals for prioritizing actions for PFAS management and trying to prioritize those, reducing the PFAS use and emissions to the environment.
All right, thank you, Ali. So here's another question. This one's for Paul. Paul, the question is, has anyone combined the use of plume stop with other PFAS remediation approaches on complex sites?
Yes. So depending on the situation, there's a lot of flexibility in where you use a colloidal carbon or in situ type technologies. So for particularly high concentrations, you could couple it with source removal, capping. Active systems could also be used in the vicinity where you're planning to apply a colloidal carbon barrier. And Grant Carey published a look at some modeling, options, kind of getting at this idea that you can string together a few different options especially on large complex sites where, just by necessity, you're going to need a variety of approaches to get at the problem.
Okay, thank you, Paul. So here is another question for Ali. And Ali, the question is, what's the role of remediation professionals in supporting PFAS source reduction and phase out efforts?
Yeah, I love this question because I think it's a forward-looking question. I know there's a lot of remediation professionals out there that care about PFAS in the environment and want to do their part. I think environmental remediation is professionals in this world have a lot of experience dealing with really complex situations. Sites are all different. There's multiple contaminants. There's multiple complications. There's multiple client needs. And so I think in remediation professionals have a lot of experience at looking at complex things and potentially solving problems. like this. I think there will be a significant market in terms of technical assistance to companies that are looking to report their PFAS, whether that's through state or federal requirements, and also to companies that are looking to go upstream in their supply chains to better understand where their PFAS is coming from. And while the technical skills for remediation professionals are not necessarily directly transferable, I think that understanding of complex problems and asking the right questions and understanding the nuances of different sites and different clients in different locations, I think those types of skills would be very useful in that type of technical assistance in helping companies try to figure out how to manage PFAS coming into their products, how to manage reporting to federal agencies, and how to manage processes to help phase out PFAS.
All right, and then here's another question for you, Ali, and it is, if people get less than 20% of their exposure from drinking water, then why is there so much focus on regulating PFAS in drinking water?
Yeah, I ask this question myself on a regular basis. I think it's because in the United States, the Environmental Protection Agency has direct authority to regulate contaminants in drinking water. So I'm not saying that it was easy to get the MCLs passed, but it's relatively straightforward for the EPA to say, here's how much PFAS we think can be in drinking water, and thus we're going to regulate it. Now, the EPA also acknowledged that, about 20% of exposure comes from drinking water in their risk calculations. I think the regulatory clout that you would need to implement PFAS use restrictions on the federal scale is significantly higher, because there would be a lot more pushback, I think, from companies using it and from consumers potentially. And due to its ubiquity, it's just going to be a complicated beast. So again, I think the focus on drinking water is partly just because it's simple from a regulatory standpoint. I think I hope that eventually there is a federal regulations in the United States for broad PFAS use restrictions. I think for now we're going to have to rely on specific states like Minnesota, Maine, Washington, and also on the EU to try to see how the PFAS use restrictions that are undergoing implementation right now, how those go, and then hopefully other states and the U.S. federal government can learn from those and feel more comfortable implementing broader PFAS use restrictions at bigger scales.
Okay, I think we have some more time here. So I wanted to offer another question kind of related to what you just talked about, but regarding the food intake. The question is, if there's a significant percentage of PFAS coming from food intake, what does that look like? What does that represent?
Yeah, and food intake is something that is the biggest exposure, and luckily, it's probably something that people can do something about on a personal level in terms of controlling your personal intake of PFAS into your body. PFAS that's on food can come from a variety of different places. One that people talk about a lot is if there's PFAS in the soil, either from soil contamination or from application of wastewater biosolids, for example. Potentially there could be uptake into agricultural plants that people would eat. So I think that's potentially a source, but there's a lot of work being done in this area on plant uptake to understand how significant that is. I think probably a more significant source is PFAS in pesticides. There was a study that came out recently demonstrating that a large proportion of active ingredient in pesticides are actually PFAS. And so if you're eating food that has pesticides applied to it, you are taking in more PFAS. This is one of the reasons that I've recently moved to trying to only buy organic produce. Another source of PFAS to food is through food packaging, and there have been efforts to phase PFAS out of food packaging, and I think those are ongoing. It's a little bit challenging because in the food packaging world, there's a lot of move towards compostable packaging, which is mostly like paper-based or fiber-based, but those things are typically not water resistant or grease resistant, and so you need something like PFAS, or like there's other waxy substances you could use to make them water and grease resistant. So, PFAS, if you're eating more food out of food packaging like that, either, whether it's plastics, which also have PFAS, or whether it's kind of treated paperboard product, you're probably getting more PFAS into your body. Again, it depends very much on the specific products you use and whether or not those ones have PFAS, but that is hard to know. So, I mean, if you're buying whole foods and they're organic foods from the store, you're cooking them in your house and storing them in glass containers, you're gonna have a lot less PFAS in your diet, I think, than people who are eating conventionally grown produce, potentially buying more produce from other places where they're in contact with food containers, or eating more frozen things that are in food containers. Again, I think this is an area where people really have more agency to control their PFAS exposure.
All right, thank you very much, Allie. So that is going to be the end of our chat questions. If we did not get to your question, someone will follow up with you. If you'd like to learn more about remediation solutions from Regenesis, please visit regenesis.com. Thanks again very much to our presenters, Dr. Allie Ling and Dr. Paul Erickson. And thanks to everyone who could join us today. Have a great day.